Good morning. So there is one part of this chapter that I skipped, if you remember, and that's called the pigeonhole principle. But before going to that, I saw that there is one problem regarding probabilities in the book that you need to use combinatorics to solve it. So let us try to understand that problem. So let me ask you, of course, if you have a fair coin and then you toss it once, the probability of getting heads up or tails up are both equal to 1/2. Yes? But now let us assume that we have two of these coins, and then I toss both of them, and then I ask what is the probability of both of them actually turns out to be heads. So what's the answer to this question? So that if I have one coin, the probability of one coin turns out to be head and turns out to be tails if they are actually equal, if that's a fair coin, meaning the probabilities are the same, so you expect that this is 1/2 and that's 1/2. Now my question is that you have two of these coins and toss both of them, and then you want to see what is the probability of both of them turns out to be heads. Yes?
You multiply those two.
Yeah, let's multiply, because in principle, if you have two random event that they are independent from each other, you can calculate the probability each one of them and then multiply them. So, for example, if I say the probability of both of them to be head, let me just use this symbol for saying that the first one and the second one turns out to be heads. So what's the probability of that one? That's 1/2 times 1/2, which is 1/4. And then, of course, if I ask you what is the probability that the first one turns out to be heads and the other one turns out to be tails, what is the answer to this one? Yeah?
The same.
Yeah, that's the same, yes? That's 1/2 times 1/2 is equal to 1/4. So this means that for all possible scenarios that we have, so if I say the first one tails, the second one heads, and of course the answer is the same. And then what is the probability of both of them turning up tails is also 1/2, 1/2, 1/4. And that's, by the way, these are the only possibilities if I have only two coins available, and then you see that if I add these numbers, they again become 1, yes? So that's clear that at least one of these happens. Now, the question mentioned in the book is that, let us now say, let me start with a simple example to generalize that. Now I have 3 coins of that type, and I toss all of them, and then I ask myself what is the probability of 2 of them turns out to be heads. Okay, so then how can I answer this question? So I have 3 coins, I don't know, coin 1, coin 2, and coin 3. Okay, this has the possibility to be heads or tails, heads or tails, heads and tails, yes. Now, I toss all of them. My question is that what is the probability of exactly 2 of them turn out to be heads? How do you think about the problem? I don't want you to give me the exact answer, but tell me how to proceed. Yes?
I guess it will be how many combinations you can make for that too.
Exactly. That's related to the combinatorial problems that we have. For example, can you mention one of the possibilities? When I say 2 coins turn up to be heads, it means, for example, one possibility is that the coin 1 and coin 2 turns out to be heads, and because I ask in the question the probability of exactly 2 of them turn out to be heads, then you realize that, okay, when the first one and the second one are supposed to be heads because of the problem, the third one should be the tail, yes? So, okay, but let us try to understand that problem. So you say that, okay, C1, C2 heads, yes, and C3 tails, okay? But this is not the only combination that makes sense in this problem. For example, another combination is what? C1 heads, C2 heads, and C2 tails, and then C3 heads. And then, for example, is there any other combination? Yes, C1 tails, C2 heads, and C3 also heads. Yes? Is there any other combination that I can achieve the goal that I have it exactly 2 heads up? No, so these are the only ones. Okay, now forget about these 2 scenarios. Can you tell me what is the probability of one of these, exactly this thing happening, meaning that the first coin turns out to be a head, second coin turns out to be a head, and the third coin turns out to be a tails? So what's the probability only of this one? Yes, it's very clear. What should I write? The probability of this one happening is 1/2. The probability of this one happening is 1/2. And the probability of this one happening is also 1/2. If you multiply them, it's 1/8. But what is the probability here? Do you agree that's the same thing, yes? If you have questions, please let me know, okay? And then I have 3 1/8 in my hand. And then I want to answer the question that what is the probability of exactly 2 of them turn out to be heads? So what should I do with these 1/8s? Add 2. Yeah, so that's the question mark is 1/8 plus 1/8 plus 1/8. And then it becomes 3/8. And that's the answer without using any combinatorial argument. So I considered these scenarios case by case, calculated the probability of each one of them, and add them up. Yes? But let me ask the same question if I increase the number of coins. Okay, for example, I want to have the same question, but the number of coins that I have is 10. Okay, so the same question. What is the probability? I have 10 coins available now. I toss all of them. And my question is that what is the probability of exactly 2 of them turning out to be heads? In principle, that's the same process. But then you have to consider more cases, and then it is a little bit disturbing. So is there any, and by the way, you see that the numbers in each case is the same, so that's a very good thing. So so if I have 10 coins, one possibility is that coin 1 turns out to be a head. So 10, this is also heads, and then 3 tails, 4 tails, and then up to C10 tails. So that's one scenario. Is that right? Okay, but if I ask you what is the probability of exactly this event to happen, what is the probability of that one to happen? By the way, I should have put probabilities here, yes? Okay, so what's the probability of this one to happen? This one is 1/2. This one is also 1/2. Meaning this is the probability of the first one turns out to be heads, the second one heads, the third one heads is also 1/2 because I'm assuming that my coin is a fair coin, and then I continue until 1/2. So this calculation is easy, 1/2 to the power of 10, yes? Because I have 10 of them multiplied together, so that's the answer. The exact number doesn't matter here, so you can keep it like this. But this is not one of the possibilities. The point is that another possibility is to have C1 heads, C2 tails, C3 heads, C4 tails, and then up to C10 tails, okay? So, but you know that the number to this one is also 1/2 to the power of 10. But the point is that how many of these items I need to consider now. In that case, it was not that hard to write them down and count them. So I wrote only 3 cases. So in this case, in this scenario, how many cases do you think I need to consider? This you should be able to answer. That's not a hard problem. So how many, for example, you can imagine that you have 10 locations registering the situation of each coin, yes? Okay, so I have 10 locations. And that, for example, for some reason, heads are important for me. So I take my marker and put 2 marks for locating heads, yes? So for example, in the first scenario, I mark these two. What does it mean? By looking at this, it means I'm considering the case in which the first and the second coins turn out to be heads, but the rest of them turns out to be tails. But that's not the only possibility. For example, for the second scenario, where do I put my crosses? I put one cross here and one cross there, yes? So is it clear for you that if I want to consider all scenarios, I need to count how many of these crosses I can do, yes? And how many of these crosses I can do? I have 10 distinct locations, and then I want to choose 2 of them to put my crosses on top of them. Okay, in how many ways I can do that? I have 10 distinct objects here, 10 distinct locations. I want to choose 2 of them. The order doesn't matter because nobody can recognize which cross comes first, which cross comes second. So that's a combination problem. So that becomes 10 choose 2, yes? So it is clear now that there are this number of these possibilities for me, but the good news is that the answer to each one of them is that fixed number, so this means that the question mark is adding these numbers, yes? But how many times? Yes? And the answer to this question is simply choose 10 choose 2, 1 over 10 to the power of 10. Some people probably write it like this. And if you are interested, of course, in the exact number, you have to calculate those numbers. Is that clear? Okay, let me give you one more example of this type, and then we can go to the new lesson. So assume that this time you roll a die, and then so you have a die, and then you roll it, and if the number that appears on the die is more than 2, you will lose. Okay? No, that's not a good example, yeah. Now let me do it like this. We have one roll, we have one die, and we roll it, for example, 5 times. So what is the probability that exactly two say 5s appear? Okay, if you don't mind, let me change this number with that number. 2 6s appear so that we can talk distinctly. So 6s appear. So how should we solve this problem?
So I think you could basically interpret it as, you could also say if you roll 5 dice one time each, so then you could see, what is exactly 2 6s? I mean, it would be similar to the previous one, wouldn't it?
No, the ideas is completely similar. I just want you to give me the numbers. For example, I have one die rolling it 5 times, and as you said, you can imagine you have 5 dice, and then you roll them once. Yeah. They are more or less, yeah, they are equivalent. But let me just try to stick to the problem that I mentioned here. So I have one die, I roll it 5 times, and I want to see what's the probability that exactly 2 6s appear. So, for example, let us consider one scenario. One scenario is that roll number 1 gives me a 6, roll number 2 gives me also a 6. But what can I say for roll number 3? Because I say exactly 2 6s. If the first one and the second one are both 6s, then it means by the problem of the word exactly, it means that the other ones are not 6. Okay, so let me write not 6 and R4 not 6 and up to R5. So there's no up to. Yes, roll number 5 not 6. Okay. Let us calculate the probability of this single event. Only this single event. But of course, this single event is not the whole possibility that I can imagine, yes? But what is the also, I'm assuming that the die is a fair die, so it means the probabilities of each face turning up is the same. So what is this? The probability of the first one turns out to be 6. What's that? 1 over 6. And the second one turns out to be 6 is 1 over 6. But what is the rest?
5 over 6.
5 over 6, not 6, yes? So it is 5 over 6, 5 over 6, 5 over 6. And the answer, again, the denominator, of course, is 6 to the power of 6, but the numerator is 5 to the power of 3. So that's the probability of one of these possibilities. But again, you need to consider the other possibilities, meaning that the first rolling turns out to be a 6, but the second one not 6, the third one 6, and the fourth one not 6, the fifth one not 6. This is also one possibility. And of course, if I want to write all of them, it is possible, but I don't want to do that because now I have a better tool in my hand and it's using the ideas of combinatorics. So how many of these items I can imagine? For example, let me write one of them. R1 6, R2 not 6, R3 6, R4 not 6, and I don't know, R5 not 6. So that's also and I want you to understand that the final number is the same. Do you agree? Because what I do, I will start with 1 over 6 here because I want to have 6 here. Not 6 means 5 over 6. And then again, 6 is 1 over 6. Not 6 is 1 over 5 over 6, 5 over 6. Of course, the arrangement of this product is different from the arrangement of this product, but you know that the numbers are actually the same. Yes, it becomes 5 to the power of 3, 6 to the power of 6. Yes, is that clear? Yeah?
You put 6 6s, or 6 to the power of 6 once.
Oh, okay, thank you. This is 5, yes?
Yes.
Thank you.
Babak,
Yes?
for the second one, you have 3 6s.
Not 6, not 6, not 6, 6, 6.
Oh, my mistake.
Yes. Okay, so the point is that here the numbers appear in a different arrangement, but the number of 5 6s and the number of 1 over 6s are all the same. So it means that the number at the end turns out to be exactly the same number as the previous one. And that's a good news because I don't need to be worried about different numbers appearing in each step. But now I need to count the number of these steps. So that's also clear. So what should I do? I can say that, okay, I have 5 locations. Okay, I take my marker and I can mark the locations of 6s. Or if you want, you can say that mark the locations of not 6s. Yes. So of course, the numbers, the way that you count the number of locations that you put 6s, you can say I have 5 locations. I want to choose 2 of them. You can imagine this is the number. Or you can say that, okay, I have 5 locations. I mark the locations for not 6s. Then it becomes 5, choose 3. But then we learn that these two numbers, even though written differently, they are the same. Because these two numbers add to the number of the top. Okay, so it doesn't matter how you interpret it. So then it means that the final question is this number that appears in each item. And then you have to multiply it by the number of these possibilities, which you can write this one by focusing on the location of 6s, or by this one with concentrating on the location of not 6s. So I don't know which one you prefer, so you can just write that. So is that clear? So in principle, this is a math 1C problem, so you can calculate the probabilities but then add them. The only thing that we are using is not considering these things case by case, I'm counting them by the method of combinatorics. Okay, so that is what was left. I saw it in the book, and there are some problems in the book designed by this idea. And now we go now to the page. I think it was one page and a half that I skipped, and that is called the, as the title shows here today, is the pigeonhole principle. It's called principle. Usually in mathematics, when you say something, a statement is principle, it means that we agree on it without proving it. But in principle, this is not a principle. This is a theorem, so you can call it the pigeonhole theorem. The reason that they call it principle because it seems so obvious that they say it's like a principle rather than a theorem. And the idea is clear. If you have 3 pigeons and only 2 pigeonholes, and if these pigeons are supposed to go to the pigeonholes, there is at least 1 pigeonhole containing more than 1 pigeon. Yes, is that clear? It's just, so this is so obvious that people call it a principle. In principle, you can prove it. Okay. So let me write a version of that. Okay, to save some time, let me just write it from what I have already designed. So I would say that if m pigeons occupy n pigeonholes such that m is greater than n, then there exists at least one pigeonhole containing more than 1 pigeon. Yes? It might be it's better to take this off, but of course. For example, if I have 3 pigeons, so let me write them. So pigeon 1, pigeon 2, pigeon 3, and then I have 3 pigeonholes. Sorry, 2 pigeonholes here. Okay, so I don't know, pigeonhole, let me write H1, H2 for hole 1, hole 2. If they are supposed to occupy these 2 locations, of course, this is clear that there should be at least 1 pigeonhole containing more than 1 pigeon. But it doesn't say you that there are no pigeonholes containing not more than 2, okay? Because they might decide to go all of them into 1 pigeonhole, yes? One of them is left empty, but one of them contains all of them. So these are different possibilities. But what is clear is that this is guaranteed that one of these pigeonholes has more than 1 pigeons in it. This seems a little bit ridiculous if you wanted to think about it mathematically, but believe me, there are problems that are not that easy to solve, but if you have this idea in the back of your head, you can solve the problem. For example, let me give a very simple example. If I just choose randomly 3 people, which I really don't know anything about them, do you think it is guaranteed that 2 of them at least are being born in the same month? No, because it might be the first one is born in, I don't know, January, the second one in February, the third one in March, and then I am done. But what do you think about if I choose 9 people? Can I guarantee? Of course, it might happen that if I choose 2 people, they are born in the same month, yes? It is possible, but it is not guaranteed by 2 people. So if I want to see that if I want to guarantee that I have 2 people being born in the same month, how many people do you think I need to pick up so that it is guaranteed that I have at least 2 people born in the same month? Yes?
13.
13. Do you agree? Because if I choose 12, it is not still guaranteed. If you are very unfortunate, the first person, if you choose 12, and if you're unfortunate, the first person might be born in January, the second one in February, and the last one in December. None of them are being born in that. But there is, if I choose one more, 13, definitely it is guaranteed that at least, not exactly, at least 2 of them are being born in the same day. Yes? Sorry, in the same month. So that's the idea. So that's one problem. Okay. I don't know. Could you? So for example, here, if I want to say why, I can say that, okay, if I have 13 people, I give the role of pigeons to my people, and I give the role of pigeonholes to the month of the year, and then I can assume that I have 13 pigeons, but I have only 12 pigeonholes, and according to this principle, if I want to fit them there, there is at least one pigeonhole containing more than one pigeon, which in this problem can be translated into what we desired. Is this connection clear? Yes.
Could you not like also argue that you could say that okay, I say 13 people because well, I don't know.
I said 13 because I want to have the number of pigeons
Yeah, exactly, because
somehow more than the number of pigeonholes.
Yeah, I can say because you could argue that in the worst case scenario, one person will be assigned to each month.
Yeah, exactly.
And then
Exactly,
you have
that's
one over, which will have to go.
Yeah. But I just want to make sure, because I want to start with a little bit obvious problems to see that we can solve harder problems that are not that trivial. Okay? But is that clear? So let me change the question. So how many peoples I need to choose to guarantee that at least two of them are being born on the same day of the week? 8. Yes. How many people I need to choose to guarantee that at least 3 of them are born in the same day of the week? I would say 15. Yes, because you take 7 of them, and if you are so unlucky, the first one is born on Monday, and the last one is born on Sunday next week. It's on Sunday, the end. And then the next 7 people that you choose might have the same, bring you the same misfortune, and then the first one is born on Monday. Okay, so it means that then if in the worst case scenario so far that I have chosen 18 people, each pigeonhole here, which is the days of the week, are containing exactly 2 persons in the worst case scenario. Okay, so it is not guaranteed that 3 of them are being born on the same day. But if I choose 1 person more, then this will occupy one of those. So I don't know if you're confused or not. So if I have pigeonholes here, for example, say Monday, and then Tuesday, and then up to Saturday, and then Sunday, okay? For example, if I choose 7 people, it is not guaranteed that at least 2 of them are being born on the same day. It might happen, even if I choose 2, it might still happen, but it is not guaranteed. That's the point I want you to understand. So if I choose 7 people and I am so unlucky, it might happen that the first person is born here, the second person is born here, and then finally one of them is here. So this is happening. It's not guaranteed, okay? But now I choose another 7 people here, and still assume that I am so unlucky. And then again, what happens? It means that the first one is born here, the second one is born here. So this is the worst case scenario that I'm assuming, yes? But then, how many people I have chosen so far? 14. But now, it doesn't matter. If I choose 1 person more, that person is either born on a Monday, or on a Tuesday, or I don't know, Saturday or Sunday. It doesn't matter which one. Then, for example, say I choose the person number 15, and that person is born on Tuesday. So what happens? Then I have to add 1 person here. So it means it is guaranteed that this pigeonhole contains 3 people. Is that clear? So it means that in somehow when you're dealing with pigeonhole principle, we are thinking about the worst case scenario, but it is guaranteed. So if I choose 15 people, it is really good. I don't know if you are 15 here or not. If you are 15, by the way, it's a little bit exciting. So even I don't know on which day of the work, on the which day you have been born, but if you are 15 people in this classroom, even if you don't know yourself, I can guarantee that 3 of you at least are being born on the same day. Okay, that's a very interesting interpretation. It is exactly the same pigeonhole principle. It was so obvious when I stated like that, but it is not that obvious when I'm talking it like this. Yeah? For example, I don't know. There are 2 people in the world probably having the same number of hair strands on their head. Yes? So, for example, you can guarantee that. I can say much more better because I was reading a research article about the number of hair strands because I'm getting bald today. Okay, but then I realized I think that article was saying that it goes up to 250,000 hair strands if you have a lot of them. Okay, let us assume that. But how many people are there? There are billions of people. Okay, so this is guaranteed that there are 2 people at least in the world having the same number of hair strands on the head. Okay, that's guaranteed. Yes.
Yeah, I just wanted to ask about the whole weekday thing. Doesn't like the concept of gap years kind of make, if you want to be really precise, the concept of gap years make this a bit more difficult because then
Gap years or leap
so
years?
leap years. Sorry,
Yes.
leap years.
Mhm.
How would that change the problem? I think.
I was talking about the month. I was thinking about the month, not about the days.
Month doesn't change, but maybe like if we go total.
Yeah,
days
of course.
the
In that case, you have to be careful.
It wouldn't be if we are both during the same year. Then that is a limit. But maybe if you have like a, then because we have every 4th year, you'd have to consider that has.
Yeah, I didn't say the same day of the year.
Okay.
If I want to say the same of there, if I want to be more strict, I have to mention that I don't mean a leap year or I do mean a leap year or something like that. Okay. Okay. But is that clear now? What is we are talking about? Okay. So let us make some problems a little bit more interesting. So let us consider this problem. I randomly choose 12 positive integers. Okay. I randomly choose let me say 12 natural numbers. I randomly choose 12 natural numbers. Okay. 12 natural numbers are randomly chosen. Okay. Show that among these numbers, 2 numbers have the same remainder in the division by 8. Yes. So I have 12 numbers randomly chosen. They are natural numbers. My claim is that it doesn't matter how you choose your 12 natural numbers. There are at least 2 numbers in your choices that have the same remainder if you divide them by 8. So you see that this problem is not that trivial as previous problems. So we want to see that how we can use the idea of the pigeonhole principle to answer this question. So for example, can you tell me, of course, we need calculators, but let me choose the numbers simple, okay? So I don't know, for example, 2, 7, 25, 32, I don't know, 40, 45, 80, 81, 1, 2, 3, 4, 5, 6, 7, 8, 22, 21, 16, 12. So how many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So what is the remainder of this number by 8? It's 4. What's the remainder of this number by 8? 0. What's the remainder of this number by 8? What? 5. What's the remainder of this number by 8? 6. What's the number, this one by 8?
Oh, but sorry, what is that number?
What?
What is that number?
The remainder. The remainder of
The fifth number.
this one 0.
No.
4,
The fifth number.
81.
Okay.
So, and then what is the, by the way, do you remember from number theory, what's the remainder of 2 by 8?
2.
2, yes? Because we told that if the number is smaller, that's 2. So what's the remainder of 7 by? I'm sorry, I just randomly chose them, but they haven't repeated themselves yet, yes? So what is this one?
7.
7. And then what is 25 by 8? 1. And 1 is being repeated. It's very clear now, isn't it? So it tells you that if you choose 12 natural numbers randomly, this is guaranteed that at least 2 of them have the same remainder in division by 8. Okay? But so I just want to say, first of all, tell me why. And tell me, can I reduce the number from 12 a little bit lower threshold so that I can have the same idea guaranteed? Yes? First of all, tell me why this is true. If I choose 12 number, why do you think it is guaranteed that I have at least 2 of them have the same remainder by division?
There's only 8 possible remainders of
Which are
0, 1, 2.
0, 1, 2, 3, 4, 5, and
6.
4, 5, 6, and 7. So, okay, and then I have 12 numbers. Is it clear that one of them has to be repeated? So if I want to express it in the language of pigeons and pigeonhole principle, pigeonholes, which one are playing? What is playing the role of pigeons in this problem? What is playing the role of pigeonhole principle? Yeah.
The 12 natural numbers are the pigeons.
Pigeons. So I can say that I have 12 natural numbers. So I can imagine that I have 12 pigeons, and then I would say that okay, I take the first number. If the remainder by 8 is 0, I send it to this pigeonhole. And if the remainder is 1, I send it to this pigeonhole. But because the number of pigeons is 12 and the number of pigeonholes is only 8, this is guaranteed that at least one of these pigeonholes should contain more than. So now you understand that 12 can be reduced a little bit, yes, to a lower number. So what is that threshold to guarantee the same result? Instead of 12, what can I say? 9. Is 8 enough? No. 8 is not enough. It might happen, but it is not guaranteed. Yes? So at least if I choose 9 integers, positive integers, it doesn't matter how I choose them. It is guaranteed even without looking at the numbers that at least 2 of them have the same remainder by 8. Let me ask you this question. How many numbers you have to pick to guarantee that at least 2 of them, 3 of them have the same remainder in division by 8? Yes? 17. Yes? Because if I choose 16, it is not enough to guarantee that result. Because if I am unlucky, then the first number up to number 8 will consider the remainder 0 up to 7. And the second numbers from, I don't know, the second 8 numbers will contain the same, will have the same remainders, but it doesn't matter how I have chosen. The number 17 has to choose one of these, so it becomes 3. Is that clear? Yes.
So if we want to express this mathematically, do we have to say like we assign this to be pigeon?
Usually, yes. I mean, it's good to mention that. So I would say that in this number, I can assume that these numbers are pigeons, and according to which remainder every number has when I divide it by 8, I can assign a pigeonhole principle so that you can show. I'm not very strict, but if you want to.
Okay, but as long as we refer to the pigeonhole principle,
Yeah.
then okay. Is that also how mathematicians write? Do they say I assign, if they want to use the principle, do they say I assign pigeons and holes? Do they?
Yeah, might be. Or no, might be say that according to the pigeon. It depends how advanced article you're writing or what is the who is the audience. Yes.
Okay, if it's like mathematicians writing to mathematicians, will they say pigeons? And
pigeonholes. There's no problem. Because for some reason that's famous with this. Yes. Okay, so there is one problem here. I don't know. Let us see how we can solve the problem here. Okay, so I think it's a nicer problem here. So let us assume that, let us consider a plane, and every point at the plane is colored red or blue. Of course, this is not possible because when I even put this here, that's not a point. Yes, that has that dimension. But let us assume that you have a plane, and I say that, okay, each point on this plane is either colored red or blue. Okay? Then this is a nicer question. Prove that there is at least 2 points of the same color whose distances are 1 length unit. Is that clear? So let us assume that I have the whiteboard, but of course whiteboard is a representative of plane. The plane goes forever from each direction. And assume that every point on the plane is either colored red or blue. Yes? I want to show that there is at least 2 points of the same color whose distance is exactly 1 length unit. It's a wild problem because there are infinitely many degrees of freedom. So you say the person start coloring the points, and that person start coloring the point independent of how they have done it. You can guarantee that I can find at least 2 points on the plane whose distance is 1 length unit and they have the same color. Okay, let me see if I did it right. Show that there are 2 points of the same color at distance 1 meter from each other. Yes, I thought, yeah.
So, can you choose the distance of the points when
You just randomly, I don't know what they do. So assume that there are people, one having color red in hand, one having color blue in hand, and they are actually pointing this. I just putting dots on the plane randomly. Okay. So I don't know anything about how they colored that, but I know that all the points are being colored either by red or blue. I want to guarantee, I'm sure before even coming and looking at how it's colored on the plane, I can guarantee that there is at least 2 points on this plane so that they are of the same color and the distance between them is exactly 1 length unit. Mathematical precision, not physical. So it means 1 with infinitely many decimal zeros after decimal point. So why do you think this is correct? Exactly, that's the pigeonhole principle, but it is disguised in a form that probably you cannot see. So you have to be clever enough to understand how you can connect this idea to the pigeon and pigeonholes. The idea is so simple and exciting. So that's why I call this is a very elegant problem. It's simplicity.
So if you choose a point, and then you draw the circle around it with 1 length unit radius, then either one of the points in that circle will be of the same color as the one in the middle, or there will be 2 points in that radius with 1 length unit between them, and they will also be the same color if they aren't the same color as the one in the middle.
I think that's a good idea. I haven't thought about that in that way. Well, what you are saying is that you pick a random point. So this point is either blue or red. Okay. But then you would say that, okay, so I draw a circle, yes, with radius 1, you said?
Yes.
Okay, 1, this is the radius 1, 1 unit length, so that's my radius. And then you say that, of course, there are infinitely many points on the rim of this circle. If one of them is the same color as this one, then you are done. Yes, for example, it is red. If you can find one red here, because that's also red, then that problem is solved. If this is blue and you find a blue there, still the problem is solved. But let us say if this is red, but all of them are blue, still the problem is not solved. What you are claiming is that the problem is solved from another perspective now.
Yes.
Yes.
2 points in the circle would be 1 unit.
But which points? Is it guaranteed, by the way?
I think so.
Yes.
I don't know how to print.
Yeah, but I think you are right. So what you are saying is that, okay, so let us assume that this is red, and let us assume that all these points are blue. So I lose the chance to have this one and this one to be my pair, because these are all blue, but this is red. Okay, but now you can say that I can take this one, I don't know, somehow I take it like this, and then it will take 2 points from me, and the distance between these 2 points is exactly 1 unit, yes? So I want to make sure that it is possible or not. Yes, it seems to be possible, yes? Yeah, that's, I think it's good, but it is not really connected to the pigeonhole principle. But if you write this and I cannot find any flaw in that, then I will accept it, of course. You really don't need to mention the pigeonhole principle. So are you using pigeonhole principles in somehow here? Not that obvious, but so let us think. Do you think that on a circle of radius 1, I can always find 2 points with distance 1 from each other?
Yeah.
It seems to be. That's correct. Yeah, I think I really like the idea, but that was not my way of thinking. Yes. Any other structure that you can imagine? First of all, everyone appreciate what Tino mentioned here.
Yeah.
Yeah, that's correct. The way that I was thinking was an equilateral triangle. I was thinking exactly along the lines of pigeon and pigeonhole principles. So I have an equilateral triangle with 3 vertices, yes? And I will choose this with length 1. So I would say that let us imagine an equilateral triangle, which is, this is 1 length unit, 1 length unit, 1 length unit. Okay, and I take this one and put it on my plane. Yes? Okay, what happens? How many colors I have? I have 2 colors, and I give the role of pigeonholes to my colors. Okay, so red and blue. But I take these vertices and give the role of pigeons to the vertices. How many vertices I have? 3 pigeons. And how many? So so it doesn't matter how I put this triangle on my plane. These should be colored either red or blue. So I have 3 pigeons, but only 2 pigeonholes. So it means that at least one of these pigeonholes is occupied with 2 points. So this means that distance between those 2 points is exactly 1. So that is the way that I was thinking, and it is immediately connected to the pigeonhole principles. By I don't know if you can cook up a story to connect this to the pigeon and pigeonhole principles, but I would say that if you write that one, that's completely correct. Yes, is that clear? That's also one way of saying. Is my method clear as well?
Yeah.
So I say that, okay, I construct an equilateral triangle with length 1, 1, 1. And I just put it on the plane, even randomly, okay? Then I have 3 points, but I have only 2 colors. So at least 2 of these points should have the same color. And because this is equilateral triangle with length 1, the distance exactly between those 2 points is 1. So that's guaranteed, yes? Okay, so let me see another problem here. So each point of a given straight line is dyed, I don't know, this is the way that in principle we should write this, dyed with two colors. By a color that is randomly chosen from a collection of 11 colors. Okay, so we have a collection of 11 colors, color 1, color 2, up to color 11. And then I have a straight line. And each point of this line is dyed by a color from my collection in a random way. Okay? Show that one can find 2 points of the same color on this line whose distance from each other in meters is a natural number. Yes? So I have a line, I have a collection consisting of 11 colors. I am randomly dyeing actually each point by one of these colors. We want to show that it is guaranteed if I choose 12 points, yes, am I right? Show that one can find, okay, if we have, show that one can find 2 points of the same color on this line whose distance from each other. How many points I told you that we are supposed to choose? No, I didn't say anything about that. Okay, so let me read it again. Each point of a given straight line is dyed by a color that is randomly chosen from a collection of 7 colors.
7 colors.
Yeah, 11 colors.
Yeah.
Show that one can find 2 points of the same color on this line whose distance from each other in meters is a natural number. Yes, think a little bit about it. Yes?
I guess you can choose 12 points, each of which have a distance of 1 meter between them. And then there will be, and then you assign the role of pigeonholes to the colors and pigeons to the points of the line.
Yes. So let me review what you said. So what you're saying, so you know that I have each point is colored with one of these colors randomly, yes? Okay, and then what you're saying?
You choose 12 points, each of which has 1 meter distance between them.
Yes. So you choose 12 points. It is possible. So you can imagine that you have 12 points. Yes. So the distance between them is 1 meter exactly. The distance between them is 1 meter exactly. The distance between them is 1 meter exactly. And of course, up to this is also 1 meter. So 12 points in total. Yes?
Shouldn't it be the area units, or was it expressed that the line is in meters?
Or why area units? I wanted to have the distance between 2 points. It's a distance problem.
Yeah, but like we express the distance in a unit because the distance is supposed to be a natural number.
Yes.
So it could be like 1 millimeter would also work.
No, I'm just talking about meter. But that's an obligation in the problem.
Oh, it says.
You can talk, yes.
Okay.
You can talk about millimeters if you want to. But there's also guaranteed.
Yeah, exactly.
Yeah. So now, then what?
Then the points represent the pigeons and the colors the pigeonholes.
The pigeonholes, yes. So you can say that you can assume this structure with 12 points. Each point from the other point has a distance exactly 1 meter. You can assume that this is a rod, and then you take this rod and put it randomly on your line. Yes? Because the number of points is 12 and the number of colors in your collection is 11, and if you give the role of pigeons to the points on your rod and the number of and the colors to the pigeonholes, then at least 2 of them will occupy the same pigeonhole. It means that there are but then is the problem solved?
Yes, because then it will be a natural number.
No, but might be. Let me see. So if this one and that one go to the same point, are the distance between them exactly 1 then?
It should be a natural number, not a 1. It was only a natural number, so it shouldn't be 1.
No, I don't understand exactly. So
So the distance should be a natural number in meters. So it doesn't matter if it's 1 or 2 or 3. So it should just be a natural number, right?
no, but my point is that do you believe this is one of the structures in your head?
Yes.
If I put it here, this is guaranteed that 2 of these points in your construction have the same color.
Yes.
This is guaranteed, I agree with you.
Yes.
But the distance between them is not 1 meter guaranteed.
But it shouldn't be 1 meter. It should be a natural number. That was what the problem said, right?
Exactly. So they're not, yes, that's correct. That's
What do you
correct.
mean about that?
No. I was myself confused. The problem is not asking to make the distance between 2 points to be 1 meter guaranteed. The problem was show that there is at least 2 points with the same color so that the distance between them is a natural number.
Yeah.
Okay? So if I take the Tino's structure and put it here, because the number of points that you see is 12 and the number of colors is 11, this is guaranteed that 2 of these points should be in the same color. Okay, so let us say that these 2 points are of the same color. The distance between them is 1 meter, and 1 meter is a natural number.
Yes.
Let us say this point and that point are of the same color. The distance between them is 1 plus 1 plus 1, which is 3, again a natural number. So it doesn't matter which 2 points you pick up, the distance between them is at least 1 or another natural number, which is at most 11 meters, yes? So that's correct. Is that clear? But I just want you to feel that when you look at the problem, it seems not that obvious. How can I solve the problem? But if you have the idea of pigeon and pigeonholes in back of your head, you might be able to solve that problem. So let me solve one problem and we are done. So we have a square of side 2 centimeters. Yes. So we have a square of side 2 centimeters. So this is a square, assuming that, and this is 2 centimeters. We pick 5 random points from the interior of this square. We want to show that there is at least 2 points whose distance, the points that I choose. I choose 5 random points inside this square. I want to show that at the distance between at least 2 of them. So let me show you. Prove that there are 2 points having a distance not more than square root of 2 centimeters in the points that I have chosen. So I choose 5 random points here. I want to show that the distance between at least 2 of them is less than a square root of 2, something like that. So you choose 5 points randomly inside, and then you want to show that there is at least a pair of points in the points that I have chosen whose distance between them is less than a square root of 2.
I'm imagining the worst case scenario. So let's say that one point is in the upper left corner, another one is in the upper right corner, the next one is in the bottom right corner, and another one is in the bottom left corner. The biggest distance between 2 of these points is 2 square root of 2, according to the.
Okay, so let me interrupt you. Your idea is completely correct, but people might object, why do you think this is the worst case scenario? So you need to justify this, and that needs a little bit of pigeonhole principle.
Well,
Of course, intuitively you say that, okay, I imagine this is the worst possible case scenario. I put 4 points on the corners, and then it doesn't matter where I put this point. So, okay. And then it doesn't matter where I put it. I can show that the distance between that point to at least one of those points in the corner is less than the square root of 2, somehow like that. But can you, do you feel itself it's a decisive argument that that is the worst possible case scenario? Intuitively it seems so, but can you justify it a little bit more? By the idea of thinking about points as pigeons, but try to understand what can I assign to pigeonholes here. I'm going to use your idea. So what I want to do, I want to partition my square into 4 equal squares like this. And then I would say I will give the role of pigeonholes to these 4 squares and the pigeons to points. I have 5 points. So if I want to put them here, 2 of them will go into these 2. At least 2 of them will be in one of these squares. And then, as you said, the longest line is 2 square root of 2. The diameter of each one of the smaller one is exactly square root of 2. Is that clear? So it means that no matter how I choose my 5 points, 2 of them will be actually here. In either 2 of them will be here, or 2 of them will be here, or here, or here. And it doesn't matter. In that case, the longest distance between 2 points is square root of 2. So this means that if I choose points there, yes, then it becomes a square, less than the square root of 2. That's exactly what was your idea. Is that clear? So I would say that, okay, I imagine this partition, then how many squares you see? 4. How many points you have? 5. You want to choose 5 points on these regions. But of course, I told you interior, so this means that this is included. If you want, you can say these are dots. So I am not allowed to choose points here. I'm not allowed to choose points here. I'm not allowed to choose points here. I'm not allowed to choose points here, not there. But I'm allowed to choose points on these lines. Okay, but the longest distance between the points here is the diameter of the square, because by the Pythagoras theorem it's 1 unit, it's 1 unit, so this distance is the square root of 2. Okay, so if I have 5 points chosen, it is by the pigeonhole principle guaranteed that at least 2 of them should be in one of these partitions. And the distance between those two is guaranteed to be less than the square root of 2. But that was exactly what was right. Okay, any questions? Okay, so this chapter is fully finalized. The section 2, which was graph theory, is not any part of this course anymore, so we skip that. And if you are interested to know graph theory, you can view my previous lectures and previous years. That's also a fascinating subject. I don't know why they take it off from this course. Anyway, it was more related to this course than chapter 3, because chapter 3 is differential equations, is more supposed to be math 4 rather than math 5. But probably they are knowing what they're doing. Okay, any questions?